at standing waves, and specifically what happens when you're able to create a resonant frequency and the different harmonics that are produced as you develop as well. The first thing we want to look at is the fundamental frequency. So if you were to say resonant or natural frequency is the lowest frequency at which a standing wave can exist in a medium. If you were to look at a spring that you put on the ground, for example, have two people hold either end and increase the speed until you're getting a nice standing wave that's going up and down. That is going to be the fundamental frequency, also known as the first harmonic. And there's a couple objects that might only produce a single resonant frequency, such as a tuning fork or pendulum. There's other objects where you're able to produce a large number of resonant frequencies. So if you're changing how quickly it's going to be rotating back and forth by giving it a little bit more energy, you're able to develop ones that have possibly 3 nodes, where it'll be the second harmonic. You're going to have 2 loops, and now it'll be a standing point in the middle, a node in the middle, and then nodes on either end there. And so now you'll see that it's going to be kind of like going back and forth like this. Don't worry, we'll get some better pictures in a moment as to what that looks like. I'm jumping ahead here. Suffice to say, what you need to know is that for the ropes, the strings, even within a musical instrument that have air columns, so the woodwinds, etc., you're going to be able to develop multiple resonant frequencies, which is obviously useful if you're going to be playing notes on a scale. So imagine a string placed between 2 fixed ends and it's being plucked. Most of the vibrations will interfere and disappear. There we go. The waves that have a frequency equal to one of the resonant frequencies will persist in the string. So keep that in mind. The waves that have a frequency equal to one of the resonant frequencies will persist in the string. And as you can see, there's going to be nodes on either side. In the middle, here's the antinode. So as this vibrates up and down, you have the antinode, or also known as the loop. And in this particular example, this would be an example of a fundamental frequency, or the first harmonic. This is the lowest frequency at which a standing wave can be produced. So it's a standing wave because, again, it doesn't appear to be moving along this way. All it is doing is vibrating up and down. Remember, the fundamental frequency is also known as the first harmonic, which I say right over here. So the resonant frequencies of standing waves in music are called harmonics because they harmonize. And the fundamental frequency is the first harmonic. So if we take a look at an example of a fundamental frequency, right over here, this is what it would be. So again, it's just vibrating up and down. If you were to now relate this to say, well, we know the distance between the nodes. Well, what is our wavelength? Well, the wavelength over here, you see this is only half of the wavelength. It's traveled down like this. It would need to go back down and then up again to reach the same point at which it started, signifying one complete wavelength. Here we only have half of that. So the distance between the endpoints is 1/2 of the wavelength. So whatever your distance over here is, that is equal to the wavelength divided by 2. Fundamental frequency, this is also signifying that there's one loop. This is the loop right over here, also known as the antinode. For overtones, a string vibrates in more than one segment. So this is the one that I was describing in words before. Now we have a picture in front of us. We have 3 nodes. So 2, one on either end, and then 1 in the middle here. And again, these are vibrating up and down. In this case here, we have 2 loops / 2 antinodes and 3 nodes. This is going to be our second harmonic. So the frequency of the second harmonic is twice the fundamental frequency. And so when we begin even looking at notes, if we were to say, okay, well, A4, I believe, is 440 hertz. I just double check that. Yeah, A4 is 440 hertz. So if you wanted to say, well, what is A5? That would be double that, 880 hertz. And so in that case, there A4 is not the fundamental frequency, but you get the idea. If you had a particular frequency, a certain number of hertz for your fundamental frequency, double that. That gives you your next one right there. So the frequency of the second harmonic is twice the fundamental frequency. So 2 times whatever that is. If you want to know what the third one is, it's going to be 3 times the fundamental frequency. The fourth one will be 4 times the fundamental frequency. Something to keep in mind, though, is that doesn't necessarily mean that when we're talking about note-wise, you don't necessarily go from A4 to A5. So like the fourth octave A to the fifth octave A to the sixth octave A, that doesn't happen necessarily by doubling or by multiplying by whatever value your fundamental frequency is. So it does vary a little bit. To go from one octave to the next, you're always going to be doubling your frequency here. To go from your fundamental to your second harmonic, this is the only time you're going to be doubling it. So if you're going from your fundamental to your third harmonic, well, then you're going to be tripling your fundamental, and so on. So it'll look a little bit different there. That's the key thing to remember, is that depending on what harmonic you're looking at, so if you're looking at the fifth harmonic, it's going to be 5 times whatever your fundamental frequency was to figure out what the frequency is of the fifth harmonic. The wavelength in this example here for your second harmonic is just lambda, or your wavelength. So it goes up, goes down, and then comes back to the same exact spot that, like position-wise, that the beginning was. And so you're going to have one complete wavelength. There's also two loops or 2 antinodes, as I mentioned before. Each harmonic is a whole number multiple of the fundamental frequency. So if the first fundamental frequency is 5 hertz, the second harmonic frequency would be just 2 times 5, or 10 hertz. And then the third harmonic frequency is going to be 3 times 5, or 15 hertz. And I really hope that I separated this out into overtones. Yeah. So you'll get the first taste of it here. We'll be talking about this right away. This is the second overtone. So the third harmonic is the second overtone. The second harmonic is the first overtone, so over that of the fundamental frequency. And then there is nothing before the first overtone. So you don't have anything for 0. So if we rewind to the beginning here, if you look at your fundamental frequency, there will be no overtone with your fundamental frequency. So your fundamental frequency is 5 hertz. There is no overtone. There's nothing above the fundamental frequency. If you go to your second harmonic, this will be your first overtone. It'll be 1 overtone above your fundamental frequency. And when you go to your third harmonic, that's going to be 2 over the fundamental frequency, and that makes it the second overtone. If the length of this string is L and N refers to the number of the harmonic, then this would be your formula to determine, well, what is your actual wavelength? And it all is based on whatever your harmonic number is. So if you're looking at the third harmonic, for example, because we already looked at the second one was just equal to L, and that's simple enough. If you were just to go 2 times L divided by 2, you're just going to get L. So if you're talking about, well, what's your third harmonic frequency? It's going to be 2 times whatever the length is between the nodes, and then divided by 3. So it's going to be kind of 2/3 L. It's going to look a little bit different than the previous one, right? And if you looked at even the first one was just 2 times L for the first frequency here, the first harmonic. And so to find your wavelength right over here, that's why half of the length would have been your wavelength over there. If you remember, frequency is found in the formula velocity is equal to frequency times your wavelength. So if you need to rearrange this to find frequency by saying velocity divided by your wavelength, that you can do as well. So depending on what information is given in a question, talking about fundamental frequencies, harmonics, overtones, you can begin to use that information along with the distance between the nodes to discover either the wavelength or in turn frequency. Velocity of sound is usually denoted at about 341 meters per second or 343, and that's for a specific temperature. As you increase the temperature, then that changes the speed of sound as well as the medium in which we're traveling in, or sound is traveling in. And so traditionally, we're considering sound traveling through the air medium, but if it was to travel through water, we looked at that in the past, it's a lot faster than air. So, for example, a standing wave or the second harmonic interference pattern is produced in a rope with a vibrator at a frequency of 28 Hertz. If the wavelength of the wave is 35 centimeters, what is the distance between successive nodes? So how far is it between the different nodes there? This is the second harmonic. So if it's the second harmonic, we can go back to this right over here. This would be the example of the second harmonic. So we're looking at this. This is what you should be picturing in your head here. You can always draw it out as well. I'm not sure if I did or not. I don't think I did. Not in this one anyways. But that's what you should be picturing in your head right here. So if the wavelength of the waves is 35 centimeters, what is the distance between successive nodes? Well, there was 3 nodes in that picture, and if the entire wavelength was the entire picture, actually, because that's what we had mentioned before, for your second harmonic, that's going to the distance there of the wave is 35 centimeters. That whole length is 35. So if it's in between nodes, you're going to have half of that value. It's only going to be 17.5 divided by 2. Anyways, what we have under this column here, these numbers over here represent the harmonic. And so please just write that down. This represents which harmonic this is. So for this first picture here, it's the first harmonic or the fundamental frequency. This would be the second harmonic, the third harmonic, fourth, fifth, and so on. On this side right over here, if you were to make a guess, the first doesn't have any value at all. Then it goes 1, 2, 3, 4, 5, 6. If you guessed that these numbers represent the overtone, you would be correct. So if you're looking at the second harmonic, that's the first overtone. If it's the third harmonic, it's going to be your second overtone. So this is 2 tones above the harmonic frequency, or sorry, the fundamental frequency. This is a third overtone, fourth overtone, fifth, and sixth overtone. So these numbers represent the overtone, these the harmonics. And you can begin to see like how it actually changes the wavelength, etc. Right? So in all these examples here, like the sound isn't going to change if the medium is exactly the same. So if sound is still traveling through, say, the string or through air, in either case, you're not going to have the sound traveling in any difference. So what you're going to have is a change in your frequency and a change in your wavelength. So you notice that as you're coming from here to here, your wavelength changes, right? It's no longer as long as it was over here or as long as it was over here. Here your wavelength is the largest, and over here your wavelength is the smallest. And your frequency also changes too. So with the largest wavelength, you're going to have a smaller, not as large of a frequency, and then as you go over here, your frequency increases. And if we link this back to sound now, so if you're going to increase your frequency, that's also going to increase your pitch. So you're going to go from low to high, and that's what increasing your frequency is going to look like. The numbers have changed now, and these 2 categories are as follows. The category on our left in this case is the nodes, and the category on the right, if you guessed it, the units is hertz, so it's in frequency. So here we have 2 nodes, one on either end. Here we have 3 nodes with one in the middle and one on either end. Here we have 4 with 1, 2, 3, and 4. And you can see the very last one there. If you counted those all up, you're going to have 8 separate notes. With your frequency, this is just a hypothetical. So if we were to say that, hey, this represents, say, a frequency of 220 hertz, what is the next one going to look like? What's the following going to look like? So if you were to say, well, what's the second harmonic or the first overtone going to look like? It's going to be 2 times the fundamental frequency, 440. The third harmonic or the second overtone is just going to be 3 times the fundamental frequency. And the fourth harmonic would be 4 times the fundamental frequency. And then the very last one here, you see the pattern right over here. So it's times 4, times 5, times 6, times 7. And that's the way you're going to be getting the final fundamental frequency right over here. Well, not yeah, you get it. Fundamental, second, third, fourth, fifth, sixth, seventh harmonic. All right, short and sweets. I'm going to be posting up some problems and an answer key to that as well. And so that'll just give you a better picture as to what it looks like, and then you'll try an assignment on your own after that.